So what you're seeing here is that I've rewritten Newton's first law in the language that we've started using last time. And let's go look at that. What you're seeing here is that when I look at Newton's first law, it differentiates between states of zero acceleration and states of non-zero acceleration. So if I have constant velocity, I know that the acceleration is zero. Therefore, we call that force-free motion. And we said that this net force is equal to zero. And remember what we said about the net force. It's the sum of all of the forces acting on an object. And it's the effective force that acts on an object. Objects do not feel individual forces. They only feel the net force. So the net force is something that we will expand on quite a bit in the next chapter. So if I'm not at rest, or if I'm not moving at constant velocity, then the velocity must be changing. In other words, the acceleration is not zero. If you're in one of these three states, speeding up, slowing down, or turning, you are forced to be in that state. Another way of saying being forced to be in that state is the net force is not equal to zero. So we defined natural states of motion. So if you're in a state of motion where the acceleration is equal to zero, there are two natural states, rest and constant velocity. Again, why are these important? If you're in one of these states of motion, no net force is required to keep you there. What do I mean by no net force required to keep you there? Well, if you're at rest, you're going to stay at rest forever. If you're moving at constant velocity, you're going to continue moving at constant velocity forever. That means that's what we consider to be the natural states of motion. So that means here that you're in forced free motion. Forced free motion says that if you're in a zero acceleration state, the net force is equal to zero. If you're not, then you are being forced to accelerate. In other words, if you're speeding up, slowing down, or turning, then the net force is not zero here. So what I want to do now is that I want to give you some examples here. Okay, I want to give you some examples. And what we're going to do here is that I want to go in, and this is, I believe, where we were last time. I now want to go in and start interpreting what this all means. And what does it mean in everyday situation? So the first thing that I'll do here is that I'll make some arguments about, sort of like very simple situations. Okay, here we go. So let's start. So we want to look at the interpretation. Oops, it's not spelled right. Of Newton's first law. So the first natural state is rest. So I'm going to look at the state of motion of rest. Now, this may seem a little bit obvious, but we still have to state it just to be nice and clear. And so what I imagine here is that I have a water bottle. And when I think about a water bottle, of course, the water bottle has water in it. So I'm saying here that I have a water bottle. Now, if I put this water bottle at rest on a table, and then I'll say, okay, that here's my table where I placed it at rest, what we see here is that we can state pretty obviously is that if one places a water bottle on a table, it will stay there forever if nobody moves it. And that's pretty obvious. Of course it is. So what we say here, this kind of seems really obvious. So what we say here is that the bottle is in what? So the water bottle is in force-free motion. Force-free motion says what? The water bottle is in force-free motion because no net force is required to keep it there. It's just going to stay there. It's going to stay there forever. So when I look at this thing, because this is in a state of motion of rest, we know that the acceleration is zero. And if we know that the acceleration is zero, then there's no net force required to keep it there. Okay, no net force is required to keep it there. So you might say, yeah, of course, that's obvious. What's not so obvious is the second one. So if I have a state of motion of constant velocity, well, this is exactly the identical case of a water bottle. Most people don't realize that constant velocity is an identical state of motion. So I would say that most people do not realize constant velocity is exactly like rest motion. And the question is, why? Because it's a zero acceleration state of motion. It's exactly the same thing. So if I look at this, how could that be the same thing? And so what we'll do here is that we'll use the analogy of an air puck. Okay? And if we look at the air puck, how does this really typically work here if you have an air puck? Now note that the air puck could be an air hockey puck. So you have an air hockey table. And what happens on this table here is that you have the table, okay? So and what you find at this table here is that there are little tiny holes. And so what happens here is that now you have air that goes up these holes, right? So you have air pushing upwards. And so what we'll do here is that we'll come in and we'll draw a hockey puck. So if I take a hockey puck, what you're seeing here, so what we'll say here is that this is the air puck. What it does here is that the air lifts the puck up. So what we're saying here is that the puck is floating above the table. which implies that there's no friction. So to give you an idea of this, I have a video. Oops. So let me go show you my video so you can see what I'm talking about. So let me make sure I got this set up, which I do. And it goes like this.
Objects like planets will continue in their state of motion, straight line at constant speed, unless acted on by a force, like gravity, which would bend them into a curve. Now, we rarely see this on Earth, because there's always friction acting on the objects. But there are some circumstances in which we can remove friction. One of these situations is dry ice, and another is floating air hockey pucks.
So, oops, I meant to change windows. So what that video shows you here is that it shows you that you could have frictionless systems. They're rare and they're hard to actually see, so that if you were to take an air puck, this is one of the things that we did at Cabrillo. So I was teaching in the Watsonville Center, which has a hallway. So you could imagine that we have a hallway with a smooth floor. So in this case, it was a vinyl floor. And the hallway, I would probably say, it was a pretty long hallway. I'd say probably a good 50 feet. And then right here at the end was a wall. So here's a wall. And so I took the hockey puck, I turned it on. And so when you're looking at this hockey puck, when you turn it on, instead of air coming up, pushing the hockey puck off the ground, you could hear that when he turned on that air puck, it pushed air down and it raised it off the ground. So what I did now is that I went in and I gave it a push. So you know what happened? That hockey puck went all the way down. It didn't lose any speed as it was moving along the highway, not the highway, the hallway. The only reason why that hockey puck bounced back off the wall is because the wall was there. But let's say that I made the wall and I had a really good charge on those batteries. Let's say I made it 100 feet. Let's say I made it 200 feet. Let's say I made it a mile. You know what would have happened? That hockey puck would have continued to move forever. So what I'm saying here is that once the air puck is started, has started moving, it will continue in motion forever. It will continue going forever. And what that tells me here is that it's real clear, right? It's real clear. What this says here is that because I'm moving at constant velocity, I'm in a state of motion of zero acceleration, exactly like the water bottle. And because of this, the net force is zero. The net force is zero. And again, in the language that we say here is we say this, that, so if I now try to be as redundant as possible and say it in many ways, what keeps the puck moving? The answer is nothing. Nothing keeps it moving. Nothing is forcing it to keep moving. We say then that the puck is in what? Force-free motion. And why do we say that? Because no net force is required to keep it moving. Right? Nothing is required. As an example of this, you could think about a meteorite. A meteorite moving through space. Question: why does it continue moving? Why does the meteorite continue moving? It could travel for billions of years. And the answer is, again, is that because if I think about this meteorite that's going through space, if I look at this guy here, this guy continues to move through space because it's moving at constant velocity forever. So that is an example of why constant velocity is a natural state of motion. But as the video suggested here, is that in most everyday situations, we do not see constant velocity states of motion. Right? We do not see constant velocity like the air puck. Now, if I was to take the exact same air puck, so if the puck is now slid across the sidewalk, well, we know what's going to happen. What would we observe? What we would observe here is that the sidewalk is what? It has a rough surface. So when I look at the sidewalk, it's not a smooth surface, it's a rough surface. And so when I look at this guy here, what we say here is that we say that the sidewalk is rough. It's a rough surface. So when I go and I shoot a puck across it now, what you're going to see here is that as this puck moves, let's say in this direction, what we're going to see here is that the puck now decelerates. And as it decelerates, we see it slow down. So we're saying that it slows down. So what we say here is then according to Newton's first law, the puck will not slide forever here, but it will slow down and stop. Therefore, the puck is not in a natural state of motion. And then this says that something what's the something? It's friction, right? The something is friction is doing what? It's forcing, right? Something is causing this thing to slow down. It is forcing the puck to slow down. In other words, we are now saying that right in here, that this is forced motion. There must be a cause. So here we go. Slowing down. If you're not at rest or moving at constant velocity, then you must be speeding up, slowing down, or turning. Here, you're slowing down. And if you're slowing down, the acceleration is not zero. And if the acceleration is not zero, then the net force is not zero. So it does not violate Newton's first law.